Last couple of classes, we've been talking about different ways of optimizing, measuring how much or anticipating how much work we'll need to do for a given query plan in order to pick which of several equivalent query plans we should use. Today, we're going to kind of move on to a slightly more abstract topic. And by abstract, I mean something that you'll probably not need to deal with directly, but at the same time something that's really important to understand, even if just because it's one of those things that can get you into real trouble if you don't understand it. And that's a question of organization. So if I have a data set, and I need to store it. I mean, I think every one of us conceptually understands this idea that a disk, a file, is some collection of records. But at least for me, one of the really weird thoughts of this is that there's so many abstraction layers on top of these files that it's sometimes really hard to visualize exactly how that data gets represented. How does this file actually store all of the records that we want to keep in it? And more importantly, what are the trade-offs between different ways in which data can be stored? And so today we're going to talk about the actual serialization of data records. So how do you represent records on disk? And how do you group them together? And what are kind of the weird things that you need to think about when you're actually storing data on disk, in pages, on files, and keeping track of all of the information that we need to lay out. And time permitting, we're also going to talk about a crazy kind of layout that's been getting more and more popular over the last 5 to 10 years called column stores. Okay, so first off, how should we store a record? I have a record. What do I need to do to put it onto disk? Or a tuple? So what does a tuple consist of? Attribute values, excuse me. Okay, so a tuple consists of a set of attribute values, and I need to put those attribute values in disk. Now what is disk, or even what is memory? How is that data organized in memory if I have a tuple? By now, most of you have implemented some form of tuple. How do you store tuples in Project 1? Okay, so on disk we're storing them as sequences, as strings, just raw strings separated by some delimiters. And that's one way to represent the data. So, I mean, everyone's favorite format, CSV, essentially consists of a set of delimiters separating the different attributes in the file. The different attributes in the record. And then the record ends when you have a special delimiter that tells you you've reached the end of the record. So why is this nice? Why do we like this particular format? It's easy to retrieve. You don't need any special, it's standardized. CSV is such a widely used format that you have really very little to think about here, other than the possibility that one of those delimiter values might actually appear in the fields that you're looking for. And those weird corner cases are usually fairly easy to handle. So this is very nice from the perspective of the end user, excuse me, from the perspective of someone trying to write simple code. And it's also very nice because typically if you're using these kinds of record formats, the data is actually stored as a string, which means it's human readable. What are some disadvantages? What do you mean by, so there's, you said there's no logical separation between members. What do you mean by that? So let me rephrase that. It's not possible to tell where each tuple starts. Actually, it's worse than that. What if I want to get the blue record out of this? I have to scan through the entire record. So I can't, so this particular representation doesn't work very well if I want specific fields out of this record. Okay, so this is easy to work with, but potentially quite slow. At the other end of the spectrum, what if we had a huge amount of information about the type of information that was stored in each of these records? So we knew that the red record was an integer, the yellow record was a string of size at most 10, the blue record was a Boolean value, and the green record was another integer. So we have all of this information. How could we use that? Okay, so we could, you're actually skipping ahead of me a little here. What if we were just storing them in terms of records? So I will get to the separation to the representation you're talking about a little later today. But that representation actually requires me to do some weird reconstruction of the tuples. So even more simply, even if I just have this record laid out on disk, and I know exactly how big each value is, you can do something almost exactly similar, which is if I know where the tuple starts, and I know how big each field of the tuple is, I know exactly where to look if I want a particular field of the tuple. So if I want to access the blue record, L3, then I just add the start of the tuple to the size of the first two records, and, well, that tells me exactly where the record begins. So this is potentially quite a bit faster because, if I need just record 3, I don't have to scan through the entire tuple looking for a delimiter. Are there disadvantages to this representation? Could you speak up? Right, so the amount of space that you're using for each of these is fixed. You've got no additional, if you run out of space in that 10-character string, well, too bad. All of the data has to fit into that 10-character string, or you have to rebuild the entire file. The other potential disadvantage is that you actually now need metadata about the file. You need to store this information somewhere. It could be somewhere else in the file, it could be in a separate file, but now you need to store additional information about how this tuple is laid out, or how this record is laid out. You'll actually see this kind of thing in most database systems use a representation analogous to this, but you'll also see it in things like HBase, which just essentially create these big files laid out like this, and they keep separate organizational structures or separate catalogs storing metadata about how the file is laid out. Okay, so is there something in between? We've got this one extreme that's very flexible, very adaptable, lets me change the size of the data, lets me dynamically reallocate things very easily, but on the other hand is slow to access, versus this kind of thing that's kind of very static, very fixed, potentially a little wasteful in terms of space utilization, but is extremely efficient to access. Is there anything in between? So what's getting us the performance advantage with this layout? Fixed size. So how does the fixed size help us? Right, we don't need to scan the entire tuple to find where a given record begins. So what if we did something kind of in between and said, okay, I'm going to allow the tuple size to change. I'm going to allow the record every field to potentially vary in size, but I'm going to store, separate those values not just with delimiters, or not with delimiters, but by storing metadata for each tuple, telling me where the field begins. Now this is much less frequently used, but it's a nice way of kind of going in between. There's a couple of serialization systems that use something like this, and if you're familiar with, what's it called? Pascal. There are kind of two canonical representations of a string. One that ends with a null character, and one where the first character of the string is essentially an integer that says how long it is. This is that approach. Okay. So this is kind of the first step. How do you represent a record? Now, if I have a representation of a record, I need some way of laying these records out on disk. So every record, well, we said the level of granularity at which the disk is accessed is a page. So how do we store the records on a page? And what kind of trade-offs do we have with respect to that? Okay, so the ordering of, we can order the records in various different ways. One immediate question is whether you want, okay, so let me back up. Let's first assume that we're working with records that are nicely behaved, records that are of fixed size. So we know every single record consumes a certain amount of space. Now we can store these records in a couple of different ways. So we can, well, the first question is, do we try and squish all of the records together? So I could store all of my records in just densely packed. I keep all of them at the front of the page. And here, all I need to do to tell me which records are, well, let me back up a little. The big problem here that we'd like to solve with respect to pages is allocating new space in the page. So laying the tuples out within the page, if you're just building the pages, you fit as many tuples in there as you want. But eventually you're going to need to potentially modify those data pages. And modification introduces a new twist, which is that all of a sudden the records sitting on your page might need to go away. And if they go away, you could potentially reclaim that space, the space on that page, to store new tuples. So now if I load a page in from memory, I need to be able to distinguish which portions of the page are free and which portion where I can allocate new records and which portions are used. If you've taken operating systems, who's implemented malloc? It's a fairly common assignment. No? All right. Well, this is new stuff then. So, is everyone familiar with malloc, or equivalently new? So this is exactly the same problem that malloc runs into, which is you allocate a bunch of memory, and now that memory is marked off as used, but eventually you release the memory goes back into your pool of available memory, and this big chunk of memory is now free, and the memory management system needs to be able to keep track of where this free memory is so that it can reuse it. Anyway, getting back to this, there are two kind of, the first decision that we would need to make is how densely do we want to store these records? So at one extreme, we can take all of the records, we can store them in one big contiguous blob. And if we do that, well, we can very easily keep track of where we are in the page, and if we need to start allocating more records, all we need is a single integer that tells us how far into the page the records are. So that's good. It gives us a nice, tight, compact representation of the data records. But there's potentially some drawbacks. Why might this be less than ideal? Speak up a little. Right, so immediate problem, as soon as a record is deleted, we need to move things back into place. And that's a real pain in the butt if we're expecting these records to be in sorted order. It means we have to move everything. Same thing if the records are of variable size. On the other hand, it's nicely packed, everything is in one place, and we don't have to waste a lot of space keeping track of where the free space is. The other extreme, we can just have an arbitrary mishmash of records stored in wherever, and store kind of a bit array telling us which slots are occupied. Then if we need to allocate something new, we scan over that bitmap and find the page that corresponds to that slot, or find the first available slot in the page. Okay. Now, this bitmap approach is still somewhat decent if you have fixed size pages, because you can represent the amount of data that you can represent each of the slots as a bit vector. If you have n pages, you need n bits, 0, 1, the page is occupied or not. On the other hand, this doesn't work once you have variable sized records. So how might we go about storing building a similar index for variable sized records? Okay, so for every record, we keep some metadata telling us where each record starts and potentially where it ends. So within a page, we might keep both the records, a pointer to some empty space, and then kind of an index telling us where each record starts. Now, there's a couple of different ways of going about this, but you'll note that if I just keep track of these kind of weird, if I just keep track of where every record starts and where every record ends, it gets progressively harder and harder to allocate new memory in this, to allocate new record slots in this format. So periodically, if I have one of these representations, I'll probably want to go through all of my pages and rebuild them, moving all of the records to the front of the page, compacting them, and freeing up some memory. Right. So another advantage of this is deletions are, so this is quite flexible. It works well, and it gives me very cheap deletions because I don't actually need to modify any data. All I need to do is remove one of those pointers. Right. Okay, so we started off trying to figure out how a record would be laid out in a sequence of bytes. Now we talked about how how records get laid out in a page. And then finally, the final component here is files themselves. So a file is basically just a collection of pages, but how are those pages laid out? We talked about heap files, where the records aren't necessarily stored in any specific order, but the way that the data is stored in any order, but we might need to keep track of how just which pages are active. And typically, what we'll do here is, let me back up. So one problem we might run into is what happens when we delete all of the records in a given page, or when we start deleting records and we realize that we have 2 pages that are half full. We can compact those into a single page. In other words, the same kind of problem with holes that we get, these holes in between records that we get with when trying to store records on a page, we could get similar problems when we try and store pages in a file. So even though a heap file might be this big sequence of pages laid out on disk, some of those pages are going to be empty, and we want to be able to avoid having to load those pages into memory if we can. So we'll essentially do something almost identical. We'll keep track of which pages are allocated and which pages are not allocated by having this one directory page and creating a kind of linked list between the pages, or we can do this. So, I mean, a page is a set of, a file is a set of pages, but we don't want to have to rewrite the file every time we empty a page. So same deal. Essentially just create a linked list of these pages, and then we can go back and forth, and if we need to delete a page, then we take the page out of the linked list, we move it to the empty page list, and if we need to allocate a new page, we can do that easily as well. The other approach is just to keep pointers to all of the data pages that are active. So we have a directory page where we just list out every single page that's active, and if a page isn't active, well, we remove it from the directory page. Let's see, how are we doing on time? Okay. So why would I use one of these over the other? Or why would I've got a linked list, and I've got a directory page that just lists out a set of data pages. Why would I prefer one of these over the other? Search time. So what do you mean by that? Constant complexity if I want to go to a specific page. Okay, so if I have some information about how the data is laid out, I probably want to use a directory page. For a heap file, if the data is completely unsorted, is there an advantage or disadvantage to one of these? So do we get any other benefits from let me ask you this. A linked list, do we have any guarantees about where the pages are on the disk? No. I mean, a linked list, every page is eventually going to be, completely random. Now, the data on those pages is completely random. We can reorder the accesses in whatever order we want. Question? We can reorder the accesses in, if we're talking about a heap file here, in other words, if the data is completely unsorted, then we can reorder how we access the pages however we like. Which means that if we're working with a traditional hard disk drive, there's actually going to be quite a bit of advantage if we can figure out what order to access the data in. So if we have a directory page, we know exactly which pages we're going to be looking for, and we can make sure that those pages are stored in sequential order as they're laid out on disk. We can skip over the pages that we're not interested in, but we're essentially able to scan through those pages much more effectively. The linked list, on the other hand, gives us the advantage of not having to spend quite as much time allocating memory. And it certainly means that we can have much smaller directory pages. Okay. Oh, and one other advantage is that you can do random sampling from a directory page much more easily, which is pretty much the one case where you'd want to do random access on a heap file. Okay, we got about 20 minutes left. So this is kind of meant to give you an idea of some of the weirdnesses, some of the things that come up when you're trying to actually take a data structure and represent it on disk. Peeling away some of the abstraction layers that we're fond of working with. Before I move on to the other half of what I was going to talk about today, are there any questions on just laying things out on disk? Okay, the third record representation. This one? Okay, so you've got three different representations, this CSV delimiter based approach, which is great because it's flexible. You can have as much space in between the delimiters as you want. And, well, as long as the delimiters are sufficiently unique, this works quite nicely. The downside, though, is that you can't tell where a given field starts. So if I have 50 fields and I'm looking for field number 46, I have to go through, I have to scan through 45 fields worth of data in order to find the delimiter that the location of the start of the record that I'm actually looking for. So if I'm only interested in that one record, this is going to be really slow to access, to parse out. On the other hand, I could store records in a fixed size layout. I know every time I load a record into memory, the field number 46 starts at this memory location, at this memory offset. And let's say each record is an integer. Let's go with 8-byte integers. So 46 times 8 is, I can't do the math in my head, but 46 times 8, that many bytes into the record is where record number 46 starts. So I don't have to even look at the first 46 bytes of memory. I don't have to parse it. I don't have to do any string manipulation. I don't have to do string comparisons. I know exactly where the record starts. And this is kind of a middle ground. So I don't have to, if I want to know where record 46, or where attribute 46 starts, I don't necessarily have to scan through 46 attributes worth of data. I just have to find this, look into my array at the very start of the file, find the 46th offset in that array, and I know exactly where the 46th offset is, because they're offsets, they're not strings, they're integers, not strings. So I know exactly where that is, and then I can jump directly to the byte where the attribute that I'm interested starts. So I pay 2 memory accesses rather than however many however many bytes there are until I get to the delimiter I'm looking for. Does that address your? Yeah. This one?
Yeah. So I did not understand how the pages will be stored sequentially in the second one.
Okay. So the basic gist of it is this. Let me diagram this up a little. So ostensibly, a file is one really big, long sequence of bytes. Now, for convenience and ease of memory access, we typically divide this big file up into pages, right? So I'll start writing things to my file, writing more stuff to my file, putting data in each page. And, time goes on, the pages start getting full. And I might delete some stuff, delete some more stuff, write a few more things, delete some more stuff. And eventually I might realize, hey, wait a minute. The data here is not very dense. I could get quite a bit more benefit, or I could essentially skip this entire page if I moved all of that data to this page. And this will happen, basically compaction. Now, I have this one big page here that's sitting in the middle of my file, and I can skip it every time I access the data, but I want to be able to know that I can skip it. Now, I could do that in one of a couple of ways. The first thing I could do is take all the data in the rest of my file and kind of move it up here. Take this, move it up here. That's going to require copying an entire page of data to, from here to here. Maybe that's something I can do. Frequently, though, that's going to be a fairly expensive operation, and it's not something that you want to do on a regular basis. So option number 2, add a little bit of metadata to this guy saying, OK, when you get to this page, just jump over it and go to this page. But now you have this other problem. This page over here is dead. And if I want to start writing more and more data, I mean, basically I've got a free page here that I can eventually start copying data into. That's what this directory page is meant, in the linked list case, is meant to represent. So I've got one pointer to the first page that actually contains data, and I keep a separate pointer to these free pages. So if I need more space, or if I have some time to start collapsing the data together, I can do that. OK, so that works perfectly well until I start writing more data in here. And now if I want to put this back into my linked list, I can either traverse the entire array, which is going to be slow, or I can essentially update my pointer here, point to this guy, and now have this guy point back here. Now I'm sure you can imagine, after a whole bunch of manipulations of this form, this linked list is going to go all over the place. So instead, the other approach is to forget this linked list and just have a directory page that says, OK, you've got data here, you've got data here, you've got data here. Which one? That one. You got data here, you got data here, and you got data here. Now, because all of my pointers are sitting in this one page, I can do a quick sort over those pointers. Even if the pointers are out of order on this directory page, it's much easier for me to sort the pointers on this directory page so that I can guarantee that when I actually do access the pages, I access them in order. And it's much easier for me to do that if I've got all of my pointers in this one list than if the pointers are arranged in a linked list. On the other hand, this means that now every time I want to access a page in this disk, this file, I need to keep a pointer to every single page in this directory page. And if this directory page gets sufficiently large, I may need to have more directory pages. Because these directory pages are going to be probably allocated at the end of the file, that means that that doing an access on the directory page is essentially going to be a random lookup. So storing this is potentially going to be just maintaining the directory is going to be a lot harder, which is why this is not always the best approach. Does that address your question?
How would you find the free space in this case?
Same thing. You have one list of available pages and one list of unavailable pages. Or equivalently, because you know which pages are data pages, and potentially you know how big the file is, then you can basically scan through and find the pages that are missing from that list. again, depends on whether you want, whether you have a preference for using space or time as a resource.
And is it required to sort the pointers?
No. I mean, if you don't sort them, then you get random access.
On what parameter are they sorted?
I mean, presumably you want to sort the pointers based on where they are in the file. I mean, the main advantage of keeping the directory pointers sorted is so that you can get sequential scans on the data. And just to be clear, the pointer is just a page number. So if I'm dealing with 4 kilobyte pages, this is at 0 kilobytes. This is at 4 KB. This is at 8 KB, and so forth. So just 0, 1, 2, 3, so forth. All right. Any other questions? Yeah. The main disadvantage of the directory page is that the directory page could get arbitrarily large, and if you run out of space for the directory page, you need to. So, quick back of the napkin calculation. Directory page is 4 kilobytes. Or sorry, a page is, depending on who, probably talking about 4 to 8 kilobytes of data. 4 to 8 kilobytes of data stores how many integers, or how many 8-byte integers? Uh, 4 kilobytes is 1024 times 2 to the 2 to the 2 to the 12th power bytes. An 8-byte integer is 2 to the 3rd power bytes. 2 to the 9th power is what you get. You get 2 to the 9th power integers, or about 512. Yeah. So you get 512 integers that fit in one page. Okay, so I can store 512 pages worth of data. That's 2 to the 9th. A page is 2 to the 12th. It's 2 to the 21st. Again, purely back of the napkin calculations here. 2 to the 21st data pages. And how much is that? Quick trick for you guys. Every 10 powers of 2 is one SI prefix. So 2 to the 10th is kilo, 2 to the 20th is mega, and so forth. So 2 to the 20th is a megabyte. 2 to the 21st is 2 megabytes. I don't know about you, that's a very tiny database. So typically, you're going to need more than one directory page. And if I need a directory page for every 2 megabytes of data, as soon as I get to gigabytes of data, I'm talking about thousands of directory pages. That's a lot. Whereas the linked list, if all I'm doing is sequential scans over the data, linked list makes a lot more sense. Well, again, mumble, sequential versus random access. But the gist of it is the same, that a linked list works very well if you're making only very minor modifications to the data. Although actually, there's a third option, which is just to not make modifications to the file. And this is actually something a lot of newer database companies are looking at, where all queries, all data, everything is just static files. anytime you make a change, you basically create a new static file. There's a number of advantages to that, which we'll talk about when we get into transaction processing. Okay, unfortunately, we don't have... yeah, we are coming a little bit close to the end here, so we'll pick up column stores we'll pick up column stores after spring break. Any final questions? So if I have a variable-sized record, how do you lay that out in the page? Is that the, what is the question? That's a great observation. So SQL, when you define a table in SQL, most of the canonical data types in SQL, or all of the canonical data types in SQL, have a fixed upper bound on their size. Varchar has a size, char has a size. Anytime you define a type that could potentially have a variable size, you're always required to specify a maximum size. This is, by the way, one of the reasons that tweets are the length that they are. The disadvantage to that shows up in particular when you deal with varchar and another type called blob. A varchar, frequently you have these very big varchars, 500 characters or however large, simply because the you have no clue how big these how many characters are going to go into someone's name. You're in the U.S. I forget, is it North India or South India that has the long names? South. Okay, so there's the difference. If you're in North India, South India, you have a different variable size, size for your varchar, and if you're basically it's you want to have if you have to allocate for the biggest possible name, then every record where you're storing a small name is essentially wasting space. And if you have, just going to throw out a random number here, if you have 50% of your records with where the name is 10 characters and 50% of your records where it's 30 characters, you could save quite a bit of space by compressing the shorter versions. So that's one, varchar is one case where you're basically saying to the database, I'm guaranteeing you that the variable will never exceed this size, but most of the time it's going to be quite a bit smaller. So, all right. Have a great spring break and see everyone. The Monday after spring break, there will be a sub, but I will see everyone shortly thereafter. So enjoy.